Okay, good morning, everybody. So, in this class, we look at the Hodgkin-Huxley model of neural membrane dynamics. So, in the last class, we described the various signaling components in a neuron. So, we said neurons have dendrites, and there's a cell body and an axon, and then the neuron makes contact with another neuron at a synapse. So, now when a neuron receives signals at a dendrite, these signals propagate down the dendrites, they reach the soma or the cell body. Then at this point, there's a nonlinear phenomenon that takes place by which if this total input crosses a threshold, it produces an action potential, this sharp voltage spike called the action potential, which propagates down the axon, reaches the synapse, right? And then at the synapse, it releases neurotransmitter and makes voltage, produce a voltage change on the postsynaptic side. So this is a whole cycle. Now, the most important part of it, which is received a lot of attention, is how is this action potential generated? What is behind? What is the mechanism underlying this kind of nonlinear phenomenon? So this question was explored by Hodgkin and Huxley, British neuroscientists, back in the 60s, late 50s and 60s. So they worked out how exactly this happens. They developed a mathematical or a circuit model of how this kind of a voltage signal is developed, and that is called the Hodgkin-Huxley model, and they were awarded the Nobel Prize for that. So we talked about the neuron being into two states. One is a resting condition, a resting state, where the membrane voltage has a constant value of about minus 70 millivolts. Then when it gets excited, it produces either one or multiple action potentials repeatedly. So which is called the excited state. So a neuron can live in one of these two states. So I also mentioned that the key underlying factor behind the action potential generation is the nonlinearity. This nonlinearity comes in the form of voltage sensitive channels or voltage gated channels. Basically, these are channels whose conductance is a function of voltage, and therefore it is nonlinear. Because if a resistance or a conductance is linear, then it obeys Ohm's law. So V equal to IR or I equal to GV. But so that then which is linear. But if it is non-linear, then the G or R itself should be functions of either voltage or current. Right, and that's how here also nonlinearity comes into picture. So we'll see more of that later. So in the neural membrane, we have two kinds of channels: voltage independent channels, which are like linear conductances because they are constant conductances. Then there are voltage dependent channels, which are they obviously depend on voltage. Therefore, they are nonlinear conductances. So the key factor is this presence of nonlinear conductances. So we said there are many different kinds of ions which are involved. Both most popular ones are sodium, potassium, and chloride, so Cl minus, and a concentration gradient across the membrane of different kinds of ion channels produces a voltage because of the presence of semi-permeable membranes, right? And that formula is given by the Nernst potential formula. So we have seen this in the last class. So if you have a channel like this, right, so it can be represented as a series of a conductance and a battery. Battery value corresponds to the Nernst potential, and the conductance value is given in series to that. It must be in series because suppose the channel closes, then the current stops completely, right? So therefore, only when it is in series, channel closing means conductance is zero, so there's no passage of current, right? So therefore, it has to be a series in an equivalent circuit. So, and again, in the case of voltage sensitive channels, right, they are variable channels. So that is, they're not constantly open or constantly closed. That opening and closing keeps changing with time. So that is indicated by that arrow symbol cutting across the conductance to show that they are adaptive or variable conductances. So we talked about the Nernst potential of potassium, which is minus 77 millivolts, and this is the equivalent circuit. The Nernst potential of sodium, which is 50 millivolts, and this is the equivalent circuit. So then the leakage channels, which are constantly open or closed, are fixed, right? They can all be combined into one equivalent circuit by invoking the Thevenin's theorem. And so we're combining all this, and also if you assume that the membrane itself is like a capacitor, right? Because it's made up of two lipid layers forming an insulating sheet, so just like a capacitor. So you can combine all this into one circuit model like this. Now, the question is, how do you solve this? How do you write down the voltage current relationships for this circuit? So it's very simple. If you apply the Kirchhoff's current law, the input current going into the circuit from the top, and that current is like some current that you inject, in order to test the neural membrane. That current is equal to all these four currents: capacitive current, sodium current, potassium current, and the leakage current. Then the question is, what are all these individual currents? So that can be written like this: capacitive current is obviously C dV by dt, and sodium current is the sodium conductance times this voltage is called. So you can notice that I'm putting the inside of the cell above and outside below. The outside is the reference voltage, which is 0 voltage or ground potential, and inside is excuse me. Inside is the membrane voltage Vm. So sodium current is given as Vm minus ENA times GNA. Similarly, the potassium current is given as Gk times Vm minus Gk, and the leakage current is given as Gl times Vm minus El. So all these currents when added up gives you I external. Now the only thing that is missing here is, so GL is a constant, but GNA and GK are variable. The question is, how are they varying? So to understand that, we need to understand exactly how does the channel open and close, because when the conductance increases, it means the channel is open and current flows. When the conductance decreases, it means channel is closed, current cannot flow. So how does it happen? So we need to understand how this dynamics of switching between open closed states of a channel happens. Okay, and then how is the switching controlled by voltage of the membrane? This is what you need to figure out. So first we consider only simple kind of channels which have only two states, the open state and closed state. But in general, channels can have lots of intermediate states. But describing dynamics of such channels will become more complicated. See, in Hodgkin model, they assume very simple kind of channels which can only switch between two states. Right. So imagine a channel can be in either closed state or an open state. And from close to open, so imagine it as a reaction, right? That reaction proceeds with a reaction constant of K plus, and from open to close, this reaction, the reverse direction or backward direction, proceeds with a reaction constant of K minus. Okay, so how do you model that? Now, from your high school chemistry, the law of mass action. So where if you have a chemical A, which becomes chemical B, right, and follows a first order reaction, that process can be, the kinetics of that process can be represented like this. So minus dA by dt is equal to K forward times A, and like minus dB by dt is equal to K backward times B. So basically the forward reaction depletes A and the reverse reaction increases A, right? So this is law of mass action applied to the simple reaction. So the same thing can also be applied to this situation. So basically we are representing the open close dynamics of a channel as if one molecule is becoming another molecule and also going in the backward direction. So to describe that, let us assume that X is the fraction of channels in the open state, and therefore 1 minus X is the fraction of channels in the closed state. So this is if you take a patch of membrane which has a whole bunch of channels, and some are in open state, some are in closed state. So for that patch, we are saying that X is the fraction of channel which is in the open state. So therefore, the dynamics of transition may be described as dx by dt is equal to K minus into X, because that's the reverse direction will increase X, and where the forward direction will deplete X and decrease X. So which is minus of K plus into 1 minus X. The same equation can also be written in this form, slightly altered form, by introducing new parameters, tau and X infinity. So tau is the reaction rate constant, the time constant of the reaction, and X infinity is the steady state value to which this reaction proceeds. Okay, so where X infinity is defined as, so basically you just regroup the terms in this equation and you get this, where you define X infinity as K plus by K plus plus K minus, and tau is given as 1 by K plus plus K minus. Now, when we do that, we are basically representing, it's only a statistical description of the channel kinetics, right? So just like in mass action, you're not describing in mass action the dynamics of a single molecule. You assume a large population of molecules, and that's what and you define it in terms of concentration. And then that kinetic equation describes the behavior of a whole population of molecules. So similarly here also, it defines or describes the dynamics of a whole population of channels. Because if you look at a single channel dynamics, that looks quite very different. A single channel can be basically an open or a closed state. When it is open, it allows a fixed amount of current. When it is closed, there is no current. So it will be almost binary. Because the conductance variation of a population of ion channels is binary. So the current flow will be like this. When it is open, it allows a fixed current of, let us say, 5 picoamperes. This is for a single channel. When it is closed, it is 0. So, and also this happens very fast. So order of tens of milliseconds. Okay, so this is this is how a single channel dynamics looks, and this is how the current flowing through a single channel looks. Whereas, if you remember our description from the last class, that when action potential occurs, uh, the conductance variation, right, of the sodium potassium conductances looks like this. So this is so this orange curve is the sodium conductance variation. This shorter curve is the potassium conductance variation. So these are obviously smooth curves. They don't look anything like the sharp digital-like signal of a single channel. That is because these curves represent the total conductance of a large number of channels. Because channel gating will be desynchronized. All channels don't gate and open at the same time. So therefore, the average will be a smoother, average conductance or a total conductance will be a smoother signal, and that can be described by the statistical law, right, which is what we have just done. Now, first of all, how do you measure channel conductance? Because channel must be it's a molecule. So how do you measure that current? So there is a technique called the patch clamp developed by Zachman and Neher, for which they were awarded Nobel Prize in 1976. So by this method, you can even pick a single channel. So which is what is shown in this picture. So you can put a pipette and grab a single channel, apply a gentle suction so that the channel will be slightly sucked in to the pipette. And so there's a close contact, there's an airtight contact between the pipette and the membrane, right? And then you can measure the channel current. So the Hodgkin and Huxley haven't done this kind of method because this came much later. But they've used different methods called voltage clamp and all that. But I'm not going to into the methodology. Right. So now let us look at how you describe the voltage dependency. So so now the question is, how are K plus and K minus? So because the only thing about the channel dynamics, open closed dynamics of the channel is determined by the K plus and K minus, the rate constant. So if the open and closed dynamics are determined by membrane voltage, then that means the K plus and K minus are defined by the membrane voltage, are determined by the membrane voltage. So how does it happen? So here again we invoke go back to high school chemistry and invoke Arrhenius expression for rate constant. So the rate constant is a function of the activation energy of the reaction and the temperature and the ideal gas constant and also some kind of a factor, right? So this is a formula proposed by Arrhenius to calculate a chemical rate constant. So in the case of a neural membrane, this activation energy happens to be proportional to the membrane voltage. So that is how membrane voltage gets to influence the rate constants, and that is how it gets to influence the channel dynamics. So if you have used, look at these two expressions, K minus is a function of K naught minus, which is like a constant, times exponential of minus some factor beta times V. V is the membrane voltage. Similarly, K plus is equal to K naught plus into exponential minus alpha V. Okay, so therefore, K naught minus and K naught plus are independent of membrane voltage. But because of this exponential term, which is dependent on voltage, the K minus and K plus are dependent on membrane voltage. So if you plug these formula in the previous expressions, like this x infinity is K plus by K plus K minus, and tau is 1 by K plus K minus. If you do that, then you get x infinity is equal to this more complicated expression 1 by 1 plus K naught minus. So now you have K naught. You don't have K plus and K minus anymore. You express in terms of K naught. K naught minus by K naught plus times exponential of alpha minus beta times V. Similarly, tau, which is the time constant, is given by this more complicated expression. Now we define these two quantities, V naught and S naught, right, which are dependent on beta and alpha. S naught is dependent on beta and alpha. V naught is dependent on not only beta and alpha, but also K naught minus and K naught plus. Right, if you substitute this V naught and S naught into these expressions, you get slightly more compact expressions. X infinity is equal to 1 by 1 plus exponential minus of V minus V naught by S naught. This function, if you might have noticed, is called the logistic function, which has saturating property. That means so on one side it will go to 0, other side goes to 1, right? Also, it depends upon the sign of the S naught. So we'll see that in a minute. Tau has this expression. Tau basically looks like a bell curve. It goes to maximum at some finite value of V and goes to a low value on both directions. So if you express the same functions using hyperbolic, the tanh function instead of exponential, this will look like this, because one half of 1 plus tanh, right, is also is a logistic function. So similarly, tau can be, so you can just regroup the terms a little bit and write like this. So now let us see how these functions look like, and also what do they mean, right? Let us see what happens, how they vary as a function of S naught, right, based on sign of the S naught. So this is the expression for X infinity. What is X infinity? That is a fraction of open channels, right, in steady state, or infinite time. But actually, you don't have to wait for infinite time. It's only after about the time elapsed defined by tau, which is the rate, reaction time constant. After about tau seconds, so where does X go? What is the value of X? Right. So if S naught is positive, the velocity function will be an increasing function, as shown in this solid curve here. Right. And this cutoff point where it makes a transition is given by V naught, and S naught defines whether the function will be increasing function or a decreasing function. Okay, so and all S naught value, S naught sign tells you whether it's increasing or decreasing. S naught magnitude gives you the slope of this function. So in this curve, you see that so for S naught is positive, this increasing function. Similarly, for S naught is negative, you have this decreasing function given by the dashed line. So what that means is, when S naught is positive, channels open when you increase the voltage, increase the membrane voltage. When S naught is negative, channels close when you increase the voltage. Okay, so like shown in this dash curve. So channels that open when you increase the voltage are called activation gates or activation channels, and channels that close on increasing the voltage, right, are called inactivation gates or inactivation channels. So there's a little distinction between gate and channel. We'll come to that towards the end of the talk. Then the time constant happens to be an even function. That means so that is, it goes to a maximum at some finite value, and on both sides it decreases. Okay, so which is shown in this curve. Okay, now let us come to this concept of gates, right? So there are multiple gates in this in a given channel. So far we have been using like the term gate and the channel almost interchangeably. That means to describe the channel opening and closing, we just have to use one such equation. But it turns out that using one such variable to describe the entire channel open or close probability is not sufficient. So people invoke this idea that there are these things called gates inside a channel, and each of these individual gates, obeys a law like what you are seeing here. That is some kind of tau into dx by dt is equal to minus x plus x infinity. This kind of a dynamical law is obeyed by individual gates, right, and not just the whole channel, right? So therefore, then the probability of open probability of the gate then will determine the open probability of the whole channel, right? Which will look something like this. So this kind of an abstraction or description can be pictorially represented like this. This is only a schematic, and real channels don't look anything like this. This is only like a visualization, because real channels are a lot more complicated. So the idea is, when a channel opens or closes, right, it's not that this channel is basically a protein, right? If there is a passage for ions going from one side to another, then you say the channel is open. So then under certain conditions, the protein changes its shape, what is called a conformational change. So then if the change is such that the passage is closed, then you say the channel is closed. So point is that closing of the channel or opening of a channel or closing of a channel can be imagined to be occurring at many points inside that whole pore of the channel, right? So those notional points inside the channel, right, which tend to close the mouth of the channel, right? These are described as gates. So in a simplistic description, so you think of the channel as being controlled by multiple gates. Imagine these are like your railway signaling gates, right? So they are located at multiple points inside the pore of the channel, and you can imagine there are multiple such gates inside a channel. So now when all the gates are open, that is, the channel is open at all these locations inside the pore, then you say that the entire channel is open. So similarly, when all the gates are closed, right, you say that the whole channel is closed. Now, if you want to describe the channel open probability, right, then you have to talk about the open probability of the gates and see how to combine them, right, to define the open probability of the channel. Okay, so if a channel has k gates, so with that kind of a abstraction, let us define channel open close dynamics like this. Imagine a channel has k gates or multiple gates, and the open probabilities of all the gates are given by x1, x2, xk, and so on. So what earlier we used the word fraction of ion channels which are open. Now the fraction can also be interpreted as a probability, which is what we are doing now when we move over to the gate level and from channel. So we say that so each of the gates inside a channel has an probability associated, open probability associated with it. So therefore, x1, x2, xk are the open probabilities of different gates inside the channel. Now a channel is open, so as you can see from this picture, channel is open only when all the gates are open. So that means you have like an and relationship here. So therefore, the open probability of the entire channel is given by the product of the open probabilities of all the gates. So if we have xk, you have k gates, you have x1 times x2 times xk, right? So because channel is open only when all the gates are open. Now let us come with this general background. Let us come to defining the voltage dependent sodium channel. So it so happens that in Hodgkin's model, the voltage sensitive sodium channel is thought to have three activation gates, right, and one inactivation gate. So we talked about activation gate as being one for which S naught is positive, inactivation gate is one for which S naught is negative. So we also remember that for the sodium channel, the conductance rapidly increases, right, and then falls rapidly. So why does it happen? Because inside the sodium channel itself, there are two kinds of gates, right? There is the three activation gates and one inactivation gate. Activation gates open when you increase the voltage, and inactivation gates close when you increase the voltage. So therefore, both closing and opening variables are inside the same channel. So that therefore, to describe that, they have invoked existence of both kinds of gates within the same channel. Okay, so pictorially, I've just depicted it like this, just to visualize it, right? But let's understand that these are like simplistic cartoon pictures, because real channel will be very complicated. So it's supposed to have three activation gates, and so ideally you should have three separate variables, M1, M2, and M3. This is like X. This is like an open probability. So the notation for it is M. So ideally you should have M1, M2, M3 for each of these channels. And for this you need to have a separate variable, and that's called the gating variable. And that is called denoted by H here. So since you have, so ideally you should have four variables M1, M2, M3, and H, right, for the four gates. But here they assume that these three activation gates are identical. Okay, so that means their S0 and V0 are the same. So therefore, we can have, since the voltage across the channel is the same, right, for all the gates. So they use the same symbol M. So this is M for this, M for this, M for this, and H for this. So if that is the open probability of the channels, then the open probability of the entire channel, so the open probability of gates is M, 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 and H. Therefore, the open probability of the entire channel will be M cubed times H. Okay, now let us define that when all the sodium channels are open, right, you will have maximum sodium conductance. And let us call that value GNA max. That is for the given patch of the membrane. If all the sodium channels are open, the maximum conductance for sodium in that patch of the membrane is given as GNA max. So now, when the open probability of the sodium channels is given by m cube times h, then at any given instant, the sodium conductance is given as GNA max times m cube times h. Now the m and h are gating variables of the activation gates within the sodium channel. So therefore, dm by dt is given as, right, these two functions, right, alpha. This is very similar to that k plus and k minus, right, equation form. And so k plus and k minus in the Hodgkin-Huxley formulation, they use the expressions alpha and beta. So for the gating variable m, it is alpha m, the rate constant, which is a function of voltage, membrane voltage Vm, times 1 minus m, minus beta m times beta m, which is a function of Vm, times n. So similarly, for the h gating variable for the inactivation gate, it is alpha h of Vm times 1 minus h, minus beta h of Vm times h. Now, so that is for the sodium channel. Now, if you go to potassium channel is thought to have 4 gates, and all the four are identical, and all the 4 are activation gates. And that is pictorially represented by this in a very simple schematic. There are 4 gates, all the 4 are identical, and all are activation gates. And the gating variable for that is n. So normally you should have given separate gating variables n1, n2, n3, and n4. Then the channel open probability will be n1 times, n2 times, n3 times, n4. But in this case, they assume that all the 4 gates are identical. So you denote them using common variable. So the gate open probability is n. Therefore, the channel opening probability is n power 4. And just like before, if all the potassium channels are open, the total conductance or the maximum conductance of the to potassium, right, for that patch of membrane is given as GK max. Therefore, at any given instant, when some channels are open, some channels are closed, the actual conductance of potassium is given by GK max times n power 4, where the gating variable dynamics of n is given by dn by dt is equal to. So here the rate constants are given by alpha n, which is a function of Vm times 1 minus n, minus beta n, which is a function of Vm times n. Okay, so with this, we're all set to define the entire Hodgkin-Huxley model. So you go back to the circuit. You have capacitance and 3 conductances with their linear, the series batteries. So the 4 currents add up to I external, right? And this can be, we have written this already like this. So dCV by dt plus GNA into Vm minus ENA plus GK into Vm minus EK plus GL into Vm minus EL is equal to I external. So take all these ion channel currents, right, and then move it to the right side. Then you just have dCdV by dt is equal to all these currents. Now we know that GNA and GK are now variable, and therefore that variation is given by this formula, these two formulae. GNA is GNA max times n cube h, and GK is GK max times n power 4, where now we have more variables m, h, and n. They are given by these 3 equations. We already seen them, right? This is in the form of standard first order kinetics equations. And the rate constants here are alpha m, alpha h, beta h, and alpha n, beta n. These are dependent on the membrane voltage Vm. Okay, so what you need to complete the description is the form of these equations. So how are these alphas and beta functions dependent on the membrane voltage? So that is given by this formula, this formula. So alpha n is this, beta alpha m is this, right, and so on. Sorry, the last one is alpha h. Okay, so you have 3 alpha functions and 3 beta functions given by this formula. So now if you just want to recap the dependence of various variables, right? So you have the membrane voltage, which controls the gating variables m, h, and n. Actually, membrane voltage controls the alpha beta functions, the 3 alpha functions and 3 beta functions, which in turn control m, h, and n, the gating variables. Then m and h control the sodium conductance, n controls the potassium conductance, Then if you put these two in the original voltage equation, C dV by dt, they together control Vm and the loop closes. Because that's how the variables are dependent. And the external input current influences this whole cyclical process. Okay, so now next class I'll show you a kind of a live demo of how this program works, how this mathematical model works. But let us look at some snapshots of how the responses look like. When I start with a very small current, note that all these currents are described in terms of per unit area. We'll also define the conductances as per unit area because we said that we're not looking at single channels, but we're looking at a whole population of channels present inside a patch of membrane. So since conductances add up, right, over a patch of membrane because they're all across the same voltage, the membrane voltage. So they're all in parallel. So therefore, they just add up. So we can group them and talk in terms of conductance per unit area. So when current is very small, right, like this constant current of 0.02 microamps per mm, the voltage looks like this, right? It is just goes up a little bit and comes back to the baseline, right? And the M, H, and N, right, the curves look like this. The okay, and then the conductances, right? G, N, A, and GK, they vary like this. So there's not much change. They're almost constant. But when you increase the current to 0.023, right? So this kind of a slow variation, which is the kind of thing that you see in a linear circuit, that suddenly changes, and you see a sharp spike appearing. There's already an action potential. But only thing is, you have a single action potential which emerges, and then this dies back, right? So what you see is as you increase the current gradually. So here it's 0.02. You increase the current at third decimal to 0.023. Suddenly you see something quite abrupt, quite sudden, happening. That's a sign of nonlinearity, and you see that happening in this mathematical model. So, corresponding to this action potential, you see the conductance value is also changing suddenly, changing in sharp variations, as you can see here. And sorry, these are the gating variables, M and H variables, and these are the corresponding conductance values. Right? You see that the sodium conductance rises sharply and falls sharply. The rise is because of the activation gates, because activation gates open with increasing voltage, and fall is because of the inactivation gates, because inactivation gates close. So that will tend to. The only thing is what happens in sodium channel is the activation gates open faster than inactivation gates. It's some kind of a, you can think of it as some kind of a internal contradiction within the sodium channel. So activation gates increase the conductance, inactivation gate, the single gate within sodium channel, close the channels. In potassium channel, there's no such problem. They're only activation gates and they open. But when potassium channels open, they tend to decrease the membrane voltage. Okay, so anyway, so sodium channels open and close quickly, whereas potassium channels open slowly and also close slowly. And you see that variation here. So now if you increase the current from 0.023 to 0.1, right, which is much higher than this, you see that you have a continuous spiking activity. So here you saw only a single spike, an isolated spike, it stops. So it doesn't fire continuously. But as you increase the current, it goes to a new mode of firing, it fires continuously. And you see this classic action potential shape, a smooth rise followed by a sharp rise and then a sharp fall. Correspondingly, you see the gating variables also vary, right, like this, and the conductances vary like this. Okay, a sharp rise and sharp fall for the sodium conductance, and a slower rise and a slower fall for the potassium conductance. Now, as you increase the input current further, right, you see that uh, the the firing rate increases slightly. It doesn't increase a whole lot, but actually you can also notice that the maximum voltage to which the action potential goes starts decreasing. So here, if you look at this, the maximum voltage is up to it went up to plus 30 millivolts. But as you increase the current, right, here it came down to zero. Okay, so the maximum voltage is zero millivolts, right, and so if you go here, it is also about 30 millivolts, close to 40 millivolts. Here it came down to 30, and here it's come down to 0. Okay, so if you summarize this whole response, right, of how what is the kind of a voltage activity that you see in a neural membrane as you progressively increase the current, injected into the membrane, I external, it looks like this. For very small current, nothing happens. For slightly between, right, and at some threshold value, let us call it I1, you start seeing an action, single action potentials coming up. Then as you increase the current further gradually, when you hit a second threshold, you will start seeing not just a single action potential, but you will see continuously a continuous train of action potentials. Okay, so that is so you can think of this as bifurcations occurring inside a membrane. Bifurcation means a qualitative change in dynamics, right? When you go from this range 0 to I1 to this range I1 to I2, right? You see a qualitative change because you start seeing these action potentials. And when you go from I1 to I2 and across I2, you see a sudden change in dynamics where you see the membrane going from a single action potential to a continuously firing action potential. So you see that. Now the y-axis is actually not the action potential voltage, but it indicates the number of spikes per second. Spike is an action potential. So number of spikes per second is action potential firing rate, the frequency. So that increases also a bit slowly, right? It goes from in this model for these parameters goes from about 60 hertz to 100 hertz. And as you keep increasing it, what happens is beyond a point, the peak voltage goes down. So as it goes down further and further, it's no more an action potential. The action potential is characterized by a sharp increase in voltage, right? And beyond a point, that peak voltage keeps going down to a point that you cannot call it anymore action potential. So beyond a threshold value, another threshold value I3, you say that there are no more action potentials. So therefore, you cannot talk about action potential frequency. So you just the frequency drops, right? So this is a kind of a dynamics you see in a Hodgkin model. So what we'll do in the next class is we'll do a demo of this model, right? And we'll actually see how we can get this circuit, we can get this response plot, and we'll send you the code also, and you can play it with it yourselves and see how it responds. And also the TS Sandeep and Sundari will be preparing some demos of right how to work with the phase plane. That is, you take some sample systems, right, defined with two variables. X dot is equal to f of x comma y, and y dot is equal to g of x comma y, and make the phase plots of that and draw the null lines, find the fixed points, and analyze the stability of the fixed points, and look at the flow around the fixed point, and then see what is the response of that system, right, and how does the system evolve from some initial conditions. So they'll prepare some demo, and maybe we'll plan to have a live class, right, of that. If people have questions, we can have a live class, and we can clarify doubts. But that will be a very interesting, very important experience. There's also a kind of a function called XP plane in MATLAB with which you can work, and where you can play with this with the two variable phase plane systems. Okay, we'll also look at the Hodgkin model. So with that, we can conclude today's lecture.